So we've just shown that if we have a radioactive disintegration, or we have one nucleus turning into two other particles, we'll just say, okay, that if we call the kinetic energy of this particle kinetic energy 1, and we call the kinetic energy of this particle kinetic energy 2, then we've just shown that the kinetic energy of particle 1 divided by the kinetic energy of particle 2 is equal to the mass of particle 2 divided by the mass of particle 1. Note the change here. Okay, now that's really important, because what that's saying is if you take the ratio of the kinetic energies, the ratio of the kinetic energy of one particle to the other. So if we took a ratio, if you sort of took, this is the whole kinetic energy, if this is kinetic energy of particle 1 and this is kinetic energy of particle 2, it's equal to the ratio, the inverse ratio of the masses. Okay, so actually if we took, say, the mass, if mass of particle 2 is much greater than mass of particle 1, that would actually mean the kinetic energies are split up into the same ratio, but this would be the kinetic energy of particle 1 and this would be the kinetic energy of particle 2. So in other words, the smaller mass ends up getting the larger kinetic energy, the larger portion of the kinetic energy, okay, of the total kinetic energy. Right, so looking at that in the context of the question on page 368, the top of page 368, okay, this is uranium-238, 92, okay, this is thorium, 234 and 90, and this is the alpha particle, helium-4, 2. It doesn't matter if we put the big numbers in the bottom or top, okay? So that's what we're getting. Now, that disintegrates into these two, but the masses of these two are less than the mass of this, so we also get the extra mass out as energy, okay, the disintegration energy. So now, the question is, they're telling us that the energy that's given out as kinetic energy is 6.8 by 10 to the minus 13 joules. I hope I'm reading that right. 6.8 by 10 to the minus 13 joules. That's the excess energy that's given out, and that is in the form of the kinetic energy of these two particles. So in other words, kinetic energy 1 plus kinetic energy 2, as my friend, I'm going to call it thorium and helium. So the kinetic energy of thorium plus the kinetic energy of helium is that sum, okay? And the question is to find the kinetic energy of the helium. That's what we want to find, okay? So we use the fact that what I've just proved in the previous video. Basically, the kinetic energy of helium divided by the kinetic energy of thorium is equal to the mass of thorium divided by the mass of helium. Now, we have been given that the mass of thorium, the ratio of the mass of thorium to helium is 234 over 4. It's given in the question, but if you also look here. Okay, so what does that tell us? It tells us that the ratio of the kinetic energies of helium to thorium is 234 is to 4. Okay, so that means that the 234 is to 4. That's how the kinetic energy ratio is divided. And that much goes to the helium, that much goes to that portion goes to the thorium. Okay, now that's up to you how you do ratios. If you like, you can think about it as, well, if you divide, you can actually divide by 4, so it becomes 58, 4 into that goes 5, 4 into that goes 8, 58.5 is to 1, okay? So you can view it as that ratio or that ratio, it doesn't matter. So what you need to do now is you need to break up 6.8 by 10 to the power of minus 13 into the ratio 58.5 is to 1, okay? Or 234 is to 4, all right? Now, personally, I would stay with the whole number ratios, and I would say if the ratio is 234 is to 4, that means the total sum of the parts is 238. So this particle gets 234, 238, and this particle gets 4, 238. okay? And then I would get that fraction of this number. So 234 2/3 of 6.8 by 10 to the minus 13. And that will give you the kinetic energy of the helium particle. If you want the kinetic energy of the thorium particle, you would get 4 2/3 of 6.8. Or you take away the energy that you just worked out for alpha from the total. Okay?